Okay, so just as a review, let's look at the reaction between AgNO3 and KCl and figure out what the precipitate is going to be. So first thing we want to do is identify what the ions are. So if you take a look at AgNO3, it's an ionic compound. You should be able to identify that Ag is your cation and NO3 is going to be your anion. Okay, NO3 is one of the ones you need to memorize. It's nitrate and it's going to be a negative charge. That means Ag has to be a positive 1 charge. Everybody good with that so far?
Yeah.
Okay. Also, NO3 comes out a lot, so you'll probably just memorize it, and I'll talk a little more about that in a second. And then KCl, pretty easy. Got potassium, chloride, and then you look at the periodic table. The most common ions are K plus and C minus. Okay, so we're gonna go double replacement here. So they're going to react with the opposite one. So Ag and Cl are gonna react to form AgCl. Now we don't know the solubility rules for this because I told you there's 2 that you need to memorize, right? The first rule that you need to memorize is that all
of them in the first row.
Exactly. Column.
Yeah.
Alkali metals are always soluble.
Yeah.
And the other one that's always soluble is nitrate. So if you want to make a note of that, you can. But alkali metals, everybody in the first column will always dissolve in water. And anything with NO3 will also dissolve in water. This does not apply to either of this. So let's leave that alone for right now. And then if you take a look right here, K plus and NO3, they should form potassium nitrate. And if you look, you got an alkali metal and nitrate. So this one is going to be soluble. Okay, so this one will dissolve in water. Okay, so the parenthesis, so we could, if you want to denote the state of matter, this is, you're going to write AQ next to it just to show that it's going to dissolve in water. All right. Now the question did ask, what's the precipitate? So you can kind of guess that this is going to be your precipitate. So AgCl is your solid, and if you remembered and you scrolled up to the solubility chart that was on a little bit above in the workbook, you'll see that Cl minus is soluble except when it reacts with Ag, Hg2, and Pb. So this is going to be your precipitate. Okay, so AgCl2 will be your precipitate, and then the other compound is going to be dissolved in water. Okay. All right, so that's review from last time. Any questions on that? There are 3 different ways to write chemical equations for the solubility stuff. Now, the one that we just wrote, I want you to make a note next to it. This is called the molecular equation. A molecular equation. Okay, this is called the molecular equation. And this is typically how we write our chemical equations. Okay, but there are 2 other types of equations that have to do with this, or that are related to this. Okay, so on your notes, I just want you guys to have this, I guess, as your first row, and then we'll label the ones going downward. Okay, we're going to be using this to solve the remaining problems, though, okay, or to talk about this concept. So the next type of equation is called the complete ionic equation. Complete ionic equation. Okay. Now the complete ionic equation is exactly what it sounds like. Basically what we're doing is we're writing this equation, but we're going to write all of the ions that are associated with it. So let me erase this just so we have some space. But before we do that, let's finish up our molecular equation. We're going to finish it by writing all the states of matter. So precipitate, we did solid. This is aqueous. If you look at AgNO3, this has NO3, right? Yeah. So what's the state of matter for this? Aqueous. Yeah, aqueous. And then same thing for KCl. This is also aqueous because it has potassium in it. All right, so for the complete ionic equation, what we're going to do is we're going to write down all of the ions that are associated. So basically everything that's aqueous, we just break it down into its ions. So for AgNO3, we know that Ag is going to become Ag plus, and then we write aqueous. And then NO3 is also aqueous, so we're going to separate that off. So NO3 minus aqueous. plus this one right here. K becomes K plus aqueous. And then Cl becomes Cl minus aqueous. Okay, and you guys kind of see what's going on, right? We're just taking our aqueous ionic compounds and we're just separating them. Okay, that's why it's called a complete ionic equation. It's showing them in their ionic forms. Okay, just a heads up, on your test you will have to do this, so just a reminder to get this down. Yes. Right here. This is molecular equation, complete ionic equation. Yeah. Sorry, my handwriting is pretty dog. All right, now if you take a look, there's only one compound in the equation that is not aqueous, right? It's the precipitate. And for this one, you keep it together because this one does not dissolve in water. It does not ionize. So we just keep that molecule together, AgCl, and it's a solid, so we keep that together. Okay. However, KNO3 is aqueous, and so we have to separate the KNO3 into its ions. So this is what we have. So this is the complete ionic equation. I know it's really annoying to write because it's super duper long, but this is one of the things the AP test does check to see if you can identify what everything breaks down into. Okay, but it's not too bad as long as you know your ions. All right, any questions? Yeah. Oh. Okay, so that's the complete ionic equation. There is one last one, and for the last one, we're going to use the complete ionic equation. Okay, so give me a second. Let me erase the molecular because we used that already. Okay, the last type of equation we're going to talk about is called the net ionic equation. Okay, net ionic equation. Okay, so we had molecular equation, complete ionic equation, and then the last one is called the net ionic equation. And the net ionic equation is kind of like what the name says. It's basically what happens in the equation. What is the net product? Because if you look at the equation, there are some ions that don't really do anything, right? So if you take a look on the left and right side, do you guys see how K is aqueous here and aqueous here? It's not doing anything. This is what we call a spectator ion. Spectator ion. Okay? And the reason why we call it a spectator ion is because it just spectates. It doesn't participate in the reaction at all. Okay? There's one more spectator ion. What's the other spectator ion?
NO3.
NO3, yeah. Nitrate is also a spectator ion. So K and NO3 are spectator ions. Okay? And so what we do in the net ionic equation is we basically just don't write the spectators because they're not really important. They don't do anything. They just spectate. And so what we would do for the net ionic equation is write down the ions that actually make the precipitate. So Ag plus, Cl minus, and they produce AgCl precipitate. Okay. So that's how you can write the three different types of equations that have to do with these precipitates. Okay, and just a reminder, this will be on your test. You will have to write all three of them. I'm going to tell you, hey, this salt and this salt react together. What is the molecular, complete, and net ionic equations? Yeah. Oh, you mean going from here to here? Yeah, so for the net ionic equation, you just need to figure out what the spectators were, which ones don't do anything, and then just don't write them in the final one. Yeah. And then we're going to do an example with this, so you'll kind of see what formatting is required for the answer. Yeah, but great question. Okay, any other questions? Okay, we're going to do one in a second. Okay, let's try an example then. I'm going to scroll down. And this is all just an explanation of what we just talked about. Okay? Okay, let's do this one, 4.6. Okay, now first I want you guys to write the molecular formula. Okay, molecular formula. And this is why Again, I keep telling you, you need to memorize your polyatomic ions because sometimes they only write the name. They don't give you the formula. So take a second, take about a minute or so, see if you can write the molecular formula, and then we will go over it. If you feel comfortable going on to the net ionic and the complete ionic and the net ionic, go ahead and do that. But at least try the molecular formula. You are reacting calcium chloride and sodium carbonate. Okay? And I'll put up the answer for the molecular in just a second. Question. So you can identify what the spectators are. Just basically look on the reactant and the product side. Let's start with Ca. If you look at Ca, you see how it's aqueous here but solid here. So that does something. So it's not a spectator. But Cl is aqueous here and aqueous here. That's how you can identify it. Yeah, great question. No worries. Yeah, typically though, just a heads up, you will have two spectators. There are instances you will have one, but that's if you start with just like an ion. So if you had something like Ca2 plus NaCl, then you could have one spectator. But if you have two ionic compounds, you'll have two spectators. Yeah, great question. Any other questions? Okie dokes. Let us move on. Okay, so I'm going to skip that one. Okay, so let's get into the next big topic of this unit. There are these types of compounds called acids and bases, and we're going to talk about what their properties are, but also what they do a special type of reaction. Okay, so let's start with acids. So on your notes, I want you to write acids, and you guys don't need to write the full definition. I'll give you one that's kind of easy to remember for the AP test. But acids are very simple. Acids are compounds that release H plus in a solution. So you put acid in water, it will increase H plus. Okay, they're called proton donors because they donate protons, just hydrogen H plus. Okay, and so this is an example. You put HCl in water, it dissociates into H plus and Cl minus. If you got more H plus, that means the H plus concentration will increase. Okay, that's what acids are. So the most common type of acids that you will see, they are called monoprotic. Okay, mono means one, protic, proton, so they have one proton. So acids like HCl, HNO3, HBr, you guys see how there's one proton in there, right? One hydrogen. So they are monoprotic because they release one proton. Okay, but there are some acids that have more than one hydrogen, and they're called polyprotic, and depending on how many protons are, you have a different prefix. But the most common polyprotic multiple proton acid you'll see is H2SO4. Okay, this is diprotic because it's two. Okay, there are triprotic, but we don't really get that far into it. Okay, and so H2SO4 is special because if you guys take a look, this is called the first ionization. Okay, basically the first hydrogen ionizes. H2SO4 will release one hydrogen, and then if you take one off this one, it'll turn to HSO4 minus. Okay, and then HSO4 minus can do a second ionization, and this is where it releases another hydrogen, the second hydrogen. Okay. We'll talk a lot more about this later in the year, in the spring. I think we have like 2 months where we just talk about like acids, bases, and it's a big component of the AP test. So we'll get more into detail, but just know this for this unit. Okay, there's monoprotic and diprotic. Okay, diprotic, the difference is it releases one hydrogen at a time. Okay. Any questions about acids? Hopefully not too bad. If you took Chem already, you've probably seen acids before. Okay, let's look at the flip side. The other type of compound are called bases. Okay, now bases are a little bit different in our definition, but so write bases for me. Okay, and the easiest way I think to remember bases is that bases, they increase the OH minus concentration. Okay, and these brackets means concentration, so just keep that in mind. So they increase the concentration of OH minus in a solution. There are other definitions for acids and bases, but if you just know the ones I gave you, it'll get you through like 99.9% of the questions on the AP test. Okay. Now, there are two different ways that a base can increase the amount of OH minus. The first is really easy. It could have an OH minus and just release it into the solution. So, good example would be LiOH, things like KOH, NaOH, so on and so forth. They release OH minus, they release me into the solution. Okay. Okay, now there is one base that you do need to memorize because they like to use this to kind of trick you. The one base that does not have OH, that releases OH minus concentration is this one right here, NH3. So just make a note of that. This is ammonia. And ammonia is the one base that you're expected to memorize. It's a base that does not have OH minus. Okay. And the reason why it can increase OH minus without having OH minus is it reacts with water, so H2O. And basically what it's going to do is it's going to take one of the hydrogens from water. So NH3 becomes NH4. And then if H2O loses a hydrogen, it becomes OH minus. And by doing that, you can increase the OH minus concentration. So just make a note of it somewhere that you need to memorize. NH3 is a base. I don't remember if this is on your test, but it'll most likely be on the AP test. Okay. All right, any questions on the definitions of acids and bases, how they work? Yeah. All right, so there are different types of acids and bases. The first are called, or they're called strong acids. Okay. All right, and strong acids, the key characteristic of them is they completely ionize in solution. Okay, so basically you put a strong acid inside of water, and nearly 100% of the molecules will split up. Okay, so for example, an example of a strong acid is HCl. Okay, if you put HCl inside of water, basically 100% of the HCl molecules will break up into H plus and Cl minus. Okay, 100% dissociation. That's what a strong acid is. Okay, and the same thing for bases as well. They're strong bases as well. They're the ones that 100% dissociate. Okay, now the other type are called weak acids and weak bases, and these guys are partial dissociation. Okay, only some of the molecules break up inside of water. Okay, a good example of this that we're familiar with is vinegar. Vinegar is this right here, acetic acid. And if you put this inside of water, only some of them, oh, sorry, no minus sign, only some of them will break up into H plus and the anion. Okay, so that's the difference. It's how much dissociates. And later in the spring, we're going to be able to calculate what percentage dissociates. But for now, just know that the strongs, 100% dissociation. The weaks, less than 100% dissociation. Okay. Yeah, but you can't play right now. Huh? Oh, an actual. Yeah, I do. And the 7 strong acids you need to memorize are right here. So take a second to copy that down. I'm sorry, I don't like giving you stuff to memorize, but you just need to memorize this for the AP test. Okay, they're going to expect you to know that they dissociate completely. Okay, so just take a second, write it down. I'll show you an easy way to remember some of them. And then I'll talk about strong base in a second. But just copy these down, and then I'll explain easy ways to remember in just a second. Okay, so if you take a look at strong acids, you guys see how it's HCl, Br, and I, right? So for those ones, you can just look at the periodic table, Cl, Br, I. Okay, easy to remember those. The other ones, oops, sorry, wrong one. The other ones, I'm sorry, you just need to memorize them. Chloric, perchloric, nitric, and sulfuric. I'll be honest, if there's 2 that you don't want to memorize, these don't show up that often. They may or may not, so at your own risk, you don't have to memorize those. Mostly, it's going to be these 5 right here. ClBrI, and then NO3H2SO4. Okay, so if you get a question on the AP test that assumes or expects you to know these, I'm sorry, but I did warn you. But if you are going to skip 2 of them, these are the 2 to skip. Okay, the other ones, highly recommend you memorize them. Okay, strong bases, very easy to memorize. It's just the first 2 columns. Okay, so this column, these are all strong bases. So basically, if you have LiOH, NaOH, KOH, RbOH, so on and so forth. Okay, second column is also going to be, what is it? They're also going to be strong bases. The only difference is since they are 2+ ions, you're going to have 2 OH minuses on them. Okay, so like CaOH2. Okay, now I'm going to talk about a couple ones that they try to trick you pretty often on the test with some of the acids and bases. But any questions on that strong acids, strong bases? Okay, hopefully that helps you memorize them. But let me talk about a couple of them that the AP test brings out kind of often to try to trick you. So one weak acid they try to trick you into thinking is a strong acid is HF. Okay, and a lot of people mistake an HF as a strong acid because if you look right here, oh, it's on the same column, right? We said Cl, Br, and I are strong, but an F is right on top of it. But F is not a strong acid; it is a weak acid. Okay, so just keep that in mind. Okay, fun fact: HF is what they used in Breaking Bad to dissolve Crazy Eight's body. Yeah, HF. So this is a weak acid. Just keep that in mind. Now for the bases, one weak base that they try to trick you with is MgOH2, and a lot of people think that this is a strong base because it's in the second column, right? But this is going to be a weak base as well. And these are the ones, the 2 most common ones they try to trick you in the categorization. Okay, so the special thing about acids and bases is that when they mix, something called a neutralization reaction happens. Okay, acids and bases are basically chemical opposites of one another. So when they react together, what happens is they basically cancel each other out. Now let me, you guys don't need to copy this down, but let me give you guys the basic format of a neutralization, if I can spell it right, neutralization reaction. Okay, and then RXN, just so you know, it's kind of a way chemists abbreviate reaction. They just don't want to write the vowels, so RXN. It means reaction. So the way a neutralization reaction works, pretty simple. You get an acid, and then you react it with a base, and it's going to make water and something called a salt. And by salt, it just means an ionic compound. Okay, it's not always going to be NaCl, the salt that we eat. Okay, but by salt, it just means the ionic compound. Okay, and I'll show you guys an example, and I'll have you guys try one on your own. But this is what happens when you get an acid and a base, and they react with one another. Okay, so let's do 4.8 together. So we got our HCl, and we have CaOH2. Actually, let me color code it. It'll actually help. Hopefully, you guys see it. HCl plus CaOH2. Okay. Now, before we start, let's just test your memories real quick. Which compound is our acid? Yeah, HCl, because it has H. Okay, so this is our acid, which means this obviously is going to be our base. Okay. All right, now let's talk about the reaction, the neutralization reaction. Okay, now the first product that's always made is water, right? And we know that water is H2O. Okay, but when we write acid-base reactions, a lot of times people will like to use the formula HOH for water. Okay, it's just 2 hydrogens, 1 oxygen. It's just kind of a rewriting of it. And the reason why we like to use HOH is because let's take a look at the neutralization reaction. Basically what happens is that the H from the acid and the OH from the acid are going to react together, and they're going to make water. And so they make HOH, and that's H2O, which is water. So if you want to write HOH, I personally write HOH for these neutralization reactions. Please do that. It just kind of makes it easier to work with the reaction. You can kind of just directly see how they react. If you write H2O, you won't be penalized, but I personally think the HOH makes a little bit more sense. Okay. But that's where the water comes from. Any questions about that? Okay. Let's go on to the salts. Now, if you take a look, we just used H and we used OH to make water. The salt is basically the compound that's made with the leftovers. The compounds that the ions that are left over are Ca, okay, Ca and Cl. So the Ca and Cl are going to react together, and this is what's going to form our salt. Now, there is one thing wrong with this. Anyone know what's wrong with this formula right now? Yeah, the charges are imbalanced, right? Ca is 2 plus, Cl is minus 1. So again, this is why you got to be on top of the ion stuff. So you're going to need 2 Cls, so CaCl2. And that's how you can figure out an ionic equation. Okay. And then we need a balance, but that's pretty easy. Where is it? You just put a 2 here and a 2 here. All right, now I know the question tells you the molecular and net ionic. What type of reaction did we just write? Or equation? Molecular, yeah. We just wrote the molecular one. Okay, we're not going to do the other ones just for this example, just for the sake of time. But yeah, we just wrote the molecular. But from here, you can do the net ionic and the complete ionic as well. Alrighty. Oh, one quick thing. Sorry, I forgot the state of matter notations. HCl, because it's a strong acid, it's aqueous. This is a strong base, so it's aqueous. Okay, let's talk about the products now, the state of matter. Okay, water. The state of matter for water will always be liquid. It's going to be L. Okay. And then CaCl2. This is going to be aqueous. All right. Any questions on 4.8? I'm going to have you guys try one on your own now. Okay, and we'll actually take that one and go a little bit deeper. But everyone good with this? You guys feel okay with neutralization? Just letting you know, you will have a question like this on your test as well. So heads up. All right, let's take. Ooh, okay. I'll have you guys try 4.9 on your own. Okay, 4.9. I want you to just write the neutralization reaction. Okay, and then I'll give you further instructions later. But try to write the neutralization reaction for this problem right here. All right, guys. So let's go over 4.9. So you got your MgOH2 and HBr. Let's start by identifying the acid and base. So which one's the acid? HBr. This is your acid, and obviously this is your base. Okay. Okay. So Mg is going to react with the Br. MgBr2. Hopefully you saw that Mg is 2 plus, and then you got HBr or the H reacting with the OH to make water, and then hopefully you guys remember to balance. You got a 2 here and a 2 here. Okay. Everybody good? Okay. One thing I do want to mention, I've been a little bit lax about doing this myself, but for this unit, be very careful about including the state of matter. So if you look here, it says solid MgOH2, so just make sure you write the parentheses S behind it, and aqueous HBr. Okay, I know it's really annoying to do and easy to forget, but at least for this unit, get in the habit of doing it because it's kind of the whole point of the unit, right? Figuring out what's aqueous, what's the precipitate. So just make sure to include that.
Also aqueous, and then they do change their solid.
All right, guys. So you should have gotten this for most of the equation. I still need to do water, but you got your solid MgOH. Oh, I forgot the 2. MgOH2. So just make sure you got that for solid, and then you separate the HBr because it was aqueous. Coefficient for HBr was 2, so you need 2 for H and Br. So just remember that. I know it's a lot of things to keep track of. MgBr2 is aqueous, so we got to write that it's aqueous. And then lastly for water, water is pretty much going to operate the same way as the solids do. Since it's a liquid, we're going to just copy it down exactly the way it is. Oops, wrong color. So we're just going to write 2HOH and then label that as a liquid. All right, so that is the net ionic. Any questions about that one? Okay, the key trick here, I guess there's 3 things. Just remember solid stays together, liquid stays together, and just make sure the coefficients are consistent. Yes? This is net ionic, yeah. Oh, I'm sorry. This is complete ionic. I don't know English, my bad. English, my second language, my fault. Complete ionic. Thank you. Okay, and then now we're going to do net ionic, where we talk about the ones that actually do something. All right, now, if you take a look at the equation, what is our spectator ion?
Br and G.
Yeah, Br is one of them. Okay, is Mg a spectator? No. What is it on the reactant side? Solid. But what is it on the product side? Yeah. And so our only spectator is going to be Br minus. Okay, so a little bit different here, right? Because we got a solid as our starting. And so basically you would copy down this. So you got MgOH2 plus, and I won't color code it this time, just for sake of time. Produces Mg2 plus 2 HOH liquid. So that is going to be the molecular, complete, and net ionic. Yeah. Okay, so this is one of the more important parts of the unit. This will also come up again for our final unit, Unit 14 at the end of the year. But we start talking about it now. So there's something called oxidation reduction reactions. Okay, so I want you guys to write down this highlighted thing that I have right here. Oxidation reduction reactions. We also call them redox. So if you ever hear the term redox, that's what it's talking about. It's talking about oxidation and reduction. We'll talk about what that means in just a second, but just write that down for now. Oxidation reduction, or redox. Now, as you guys are writing it down, let me just briefly explain what they are. Redox reactions are basically where we just keep track of how the electrons move when during these reactions. Okay, so when 2 compounds react, the reason why elements react together in the first place is because of the electrons. And so oxidation reduction is a way for us to just keep track of how the electrons are moving. Okay, so there are 2 components to redox. The first is called oxidation, and obviously because oxidation reduction. And the second part is called reduction. Now, before we move on, let's talk about what it is. And the easiest way I think to remember it is through this acronym OIL-RIG. Oxidation is loss, and so whatever compound is or element is losing electrons is saying that it's being oxidized, and if it is gaining electrons, we say that it is being reduced. Okay, so let's let me just do a little bit more explaining with this. Whatever species is losing electrons, whichever one is being oxidized is losing electrons. Now, let's think about this logically. Electrons are negative, right? So if you are losing electrons, basically when you're being oxidized, you are becoming more positive. Okay, so I know it sounds backwards, right? But whatever element is being oxidized is losing electrons. It's losing something negative, so it's becoming more positive. Okay? So when you guys finish this class and you leave me, you will be oxidized because you are losing this negative influence in your life. Okay? But reduction is gain. It's when you're gaining electrons. If you gain more negativity in your life, it's like when you came into this class, right? You gained Mr. O's influence in your life. you became super negative, so you got reduced. So that means you are becoming more negative. So just keep that in mind. You might want to memorize oil rig, and if it helps, you can memorize the more positive, more negative, because it feels kind of backwards. But if you could logically deduce that, that's fine. But oxidation, you lose electrons, you become more positive. Reduction, you gain electrons, you become more negative. Okay? So oxidation is when you leave Mr. O's class. Reduction is when you started Mr. O's class. So you are in the process of being reduced. Okay? All right, so that's oxidation, reduction. Okay, so let's move on to the rules. Now, we're going to go through the rules first, and it seems really complicated, like it's a lot to memorize, but it's actually pretty easy once we start doing the actual problem. So please bear with me. I'm going to go over the rules, and you're going to have to copy them down for a little bit, but then once we start doing the actual problems, it'll become a lot easier, okay? This is a very in-depth list of all the rules. I'll tell you what's important. You don't need to know them all, okay? So the first one is pretty important. Any atom in its elemental form has an oxidation number of 0. And I'll talk about what elemental form is just in a second, but copy this down. Any atom in its elemental form has an oxidation number of 0. Okay, so let's talk about what elemental form means. Elemental form is basically how that element is most commonly found in nature. Okay, now, there are a couple things you need to remember about these, okay? Basically, all metals, the elemental form is going to be just when it's a solid. Okay, so an example would be like calcium, solid, sodium, solid, so on and so forth. Pretty much every metal's elemental form is just when it's a solid. All right, now the other ones that are pretty prominent are going to be diatomic gases. And I'll talk about what they are, diatomic gases. But a lot of the gases that we are very familiar with, their elemental form is when they're diatomic, so when there's two of them together. So good examples of these would be H2, hydrogen gas, O2, oxygen gas, N2, nitrogen gas. Okay, pretty much all of these will be, their elemental form is they're diatomic. Okay, so if you want to list them out, it'll be, I guess the most common ones are H2, N2, O2, F2, Cl2, S2, Br2. Yeah, you don't need to memorize all these, just know most of the gases are going to be, the prominent gases are going to be diatomic. All right, there is one other special one that comes up not super frequently. It's a metal. It's going to be mercury. And mercury's elemental form is going to be a liquid. This one's pretty special because mercury is the only metal that at room temperature is a liquid, so they do bring this up quite often. Just remember that. All metals pretty much are, when elemental form is when they're solids, except mercury. Okay. A couple other special ones would be carbon. Carbon's elemental form is when it's a solid. That's not a metal, but carbon's pretty common, so yeah. I'd say these are the important ones to know about their elemental forms. All right, so that's the first rule. Yes? It's what diatomic, and that is not its elemental form. Yeah. Yeah, carbon is a solid at room temperature, and so that's its elemental. Yeah. Your pencil lead is carbon. It's graphite. Okay, second rule, also pretty important. Basically, if you have an ion, a monatomic ion, the oxidation number is just a charge. Okay, so if you have K plus, the oxidation number of K is +1. If you have S2 minus, oxidation number is -2. Okay, so if it's a monatomic ion, really easy, just look at the charge. Okay, now the third one, I know there's like rules within the rule, but I'll be straight with you. The only one that you really need to know is this right here. This is probably the most important oxidation rule. Oxygen, 99.9% of the time, will be -2. And oxygen will be the one that pretty much dictates the oxidation numbers of the other elements. Oxygen is -2. Very easy to remember because oxygen's most common ion is -2. There is one exception. Comes out very rarely. I'm going to mention it so that you don't get mad at me if it comes out on the AP test. But in peroxides, basically when you have an O2 2- ion, that is the only case oxygen will be -1. Very rarely comes out. It's not going to come out on your test. So I know there's a lot to memorize. So if you want to forget something, this will be the one to forget. Okay, just remember, oxidation in 99.9% of cases will be -2. And you can use oxygen to find the oxidation numbers of everybody else. If you want to memorize these, you can, but I wouldn't. Okay. I didn't remember these rules when I was taking my first college chem classes, and I was totally fine. I just remembered oxygen's -2. Okay, guys, and the last oxidation rule is this one right here. The sum of all the oxidation numbers in a compound is equal to its charge. So for example, if you have sulfate, SO4 2-, you see how the molecule is 2-, right? If you add up all the oxidation numbers inside of SO4, it will equal to 2-. Okay, and if it's neutral like CH4, there's no plus or minus, that means they will all add up to 0. So we're going to do a couple examples now. Okay, but those are the 4 that you need to know. Okay, guys, let's take a look at 4.11. So 4.11, we got 5 different compounds, and we're going to find the oxidation number. Let's just do all of them inside of the compound. Okay, just make it easier. Okay, so we have P2O5. Okay, now, what was the most important rule that I told you about? Oxygen. What's oxygen? -2, yeah. Now, how many oxygens are there? 5. So that means all the oxygens are gonna equal to -10. Okay? Now if you look at this molecule, what is the sum of all the oxidation numbers inside of it? If you add up all the oxidation numbers in this molecule, what should it equal to?
-4.
Not -4. We said that it's the charge on the molecule. Does this molecule have a charge? No, that means they should add up to 0. Okay, when you add them all up, it should be 0. Okay, so we got oxygen, right? So all the oxygens are going to be -2. How many? We have 2 phosphoruses, right? That means these guys got to be positive, and there's 2 of them. So what does each phosphorus have to be?
5.
Yeah, 5 in order to balance it out. There you go. So the answer to this one would be P has an oxidation number. So it has an oxidation number of +5, and obviously oxygen has an oxidation number of -2. Okay, and that's how you would pretty much find those. Okay, we'll do the next one together, and I'll have you guys try the rest of them on your own. But let's take a look at B. So B is NaH. Now, if you take a look at this, it doesn't have any of the rules that we talked about, right? But there is actually a rule kind of hidden inside of it. Okay, if you guys take a look at, let's take a look at Na. Okay, this is an ionic compound because you got sodium bonded to hydrogen. What is sodium's most common ion? 1. So it's Na+. Okay, now we talked about how the oxidation number of an ion is the charge, right? So if it's Na+, what's the oxidation number of Na? 1, exactly, +1. So the oxidation number of Na here is +1. Okay, now in terms of the charge, what is the charge on this hydrogen in order to to bind with the sodium?
-1.
-1. And since it's H minus, that means that the oxidation number has to be -1. Okay, so even if you have a compound where none of the elements follow the rules, just look for the most common ion. See if there's an ion in there that you can find out, and that's how you can figure out what the oxidation numbers are. Okay, so if you take a look at C, we got Cr2O7 2 minus. Now, the key here is 2 minus. That means everything needs to add up to -2, right? Okay, what did we say the oxidation number of oxygen always is?
-2.
-2, and there's 7 of them, so that means it's going to total up to -14, right? So the sum will be -14. Okay, now, if we take a look at Cr, there are 2 Crs. So what we need to do is we need to figure out what do the Crs have to be in order to add up to -2. Okay, so yeah, it needs to be 6 each because we need them to add up to 2 or 12. 12 plus -14 will be -2, and so each of them has to be +6. So chromium has to have an oxidation number of +6. Okay. So far, so good?
Yeah.
Okay. Let's move on to this one right here. This one's a little bit tricky because, again, we don't have oxygen, right? But if you take a look at it, we have an element that we do know the MCI of. What's the most common ion that we know of in here?
F.
F. What is F's most common ion?
-1.
-1. Great. And there are 4 of them, and the sum has to be 0. So what does Sn have to be?
4.
4, exactly. Sn has to be +4. Great. Okay. And E is pretty easy. We got oxygen. What did we say it is 99.9% of the time? -2. Okay, you could have also figured this out by seeing that Ba, the most common ion, is 2+, right? So oxygen has to be -2 to balance that out. So that's how you can figure out the oxidation number.